Welcome 502 students. This tutorial is meant to take you through the orbital project that I have assigned to you. If this project seems daunting, it is. It's going to be probably a big challenge for you. There's going to be a lot of math that we have to do. However, none of the math is beyond your abilities, and we have a lot of tools that we can use to aid us. So what this project is to simply make an orbital, which maybe is a lot harder than it sounds, or maybe I'm not using the word simply correctly. But what we have to do is pick a set of quantum numbers, plug them into these equations down here, and then we can do that to generate an orbital. And we could do this for any orbital that we want. However, I'm assigning a certain number of orbitals to you. So I want you guys to make a 5s orbital, a 5p, 5d, a 5f orbital, and then also a 5g orbital, because again, remember that the orbitals are just mathematical functions that describe where the electrons are or could be, and there are plenty of orbitals that aren't represented by the lowest level electron in an element on the periodic table, and the 5g orbital is an example of that. It exists, it can be excited, an electron can be excited into that orbital, and we're going to describe it mathematically. And what I want you to do is, of course, if we have all these fives, our quantum number n is going to equal 5. And then our quantum number L will be 0, 1, 2, 3, or 4 for S, P, D, F, and G. And then for the M sub L, you can pick anything you want, but I want you to pick different numbers. So for the S orbital, M sub L has to be 0. For the rest of them, you can pick 0, 1, 2, 3, 4, pick each one once. And of course, there's going to be 4 orbitals and 4 quantum numbers, so you will leave one out. And then once you do that, you simply plug those numbers into these scary looking equations down here. And I'm going to go through an example of how to do that. And that's going to get you your orbital. So we're just going to plug in some numbers, do some math, simplify, and then we'll have a function that describes the orbital. Once we have an orbital, we're going to want to do these following steps here. So we're going to take a linear combination to make the imaginary orbital into a real one. Determine the name of the orbital, so like px, py, pz, that sort of thing. Determine the nodes, find the shape of the orbital from a list of given orbitals, plot the radial distribution function, and then determine the average radius and assemble all of this stuff as in the provided example. So it should look something like this when you're done. The example that I'm going to use is an orbital with the quantum numbers 4, 2, and 2. So 4 being a 4 orbital, L equals 2 means it's a D, so it's a 4D orbital. We have the various mathematical answers here. The radial nodes, the angular nodes, a plot of the distribution function for the radius, the shape of the orbital, and then the average position of an electron. So this is all stuff that we have done in class. We're going to put it all together and have some fun and do it for ourselves here. So here is the first equation we're going to work with. This is the radial function here. And you can see that the radial function depends on the quantum numbers n and L, which remember for my example are 4 and 2. And so all we have to do is plug 4 and 2 into this equation. So if I wanted my radial function for quantum numbers 4 and 2 as a function of r, I simply plug them into the equation here. So we'll do n minus L minus 1. So 4 minus 2 minus 1 is 1 factorial on top. And then we'll have 2 times 4 times n plus L factorial, which will be 6 factorial. Then we will have 2 over n is 4, a naught. L is 2, so 2 plus 3 halves is 7 halves. We'll take r squared, e to the minus r over 4a naught. L, 2l plus 1 is 5. N minus L minus 1 is 1. 2r over 4a naught. All right, so we have some constants out front. We have r squared, e to the minus r over 4a naught. And then we have this L thing. This L thing is a generalized Laguerre polynomial. And so this polynomial has the form L n k as a function of x. And this is something that looks scarier than it actually is. So it's this big summation here, m equals 0 to n minus 1 to the m, n plus k factorial, n minus m factorial, k plus m factorial, m factorial x to the m. So that's the scary sort of thing. But once you start plugging numbers in, it's really not that bad. So, and what we're doing here is we're making a polynomial of x, right? But our polynomial is 2r over 4a naught. So we'll plug that back in a little bit. So if we're going to go ahead and do this, we're going to make the polynomial. So we'll plug in 5 and 1. So we'll have L5, 1 of x. And then it's really just a bunch of terms. So the first term, as we go in here, right, we have, it's a summation, and we're going from m to n. So that's what this n is doing here. And k is just a constant that we're going to be using. So the numerator is n plus k, and that's always in there, right? So it's n plus k, which is 1 plus 5. So it's always 6 factorial. And then the denominator is n minus m, which is going to iterate as we sum over all of these m terms. So we have n minus m, so that's 1 minus m. So 1 minus 1 is 1. K plus m, so that's going to be k is 5 plus m is 0. So we'll have 5. And then m is 0. And then we'll have x to the 0. And this minus 1 to the m is just going to alternate. So when m is 0, it's going to be positive. When m is 1, it's going to be negative. So the next term will be minus 6 factorial. Now our m is 1, so 0 or 1 minus 1 is 0. 5 plus 1 is 6. And then m is 1. X to the 1, and we go from m equals 0 to m equals n. So now we have here, this is our m equals 0 term, this is our m equals 1 term, and it's also our m equals n term, so we're done, and that's our polynomial. So our polynomial is simply 6 factorial divided by 5 factorial times x to the 0, which is 6. And then our other one here is 6 divided by 6 times x to the 1, so it's 6 minus x. So we have this big scary looking function. And in this particular case, that polynomial is just 6 minus x. Obviously, the more n terms you have, so the bigger n minus L minus 1 is, the more you're going to get, which is going to correspond to more radial nodes. And we'll see that here. So this is our L5, 1 as a function of x, but we want it as a function of 2r over 4a naught. So that's pretty easy to do. So we'll just go L5, 1, and I'm going to now just say this is r over 2a naught, because of course 2 divided by 4 is 1/2. And then I just plug that in for every instance of x. So this is going to be 6 minus 2, or yeah, r over 2a naught. And the way that I want you to present this data is in whole numbers. This will give us similarities to the orbitals as listed in the textbook. So we're going to divide both of these by 1/2. And that's going to give us 1/2 12 minus r over a naught. And this is how I want you to present this. So this is our polynomial function here. And for the rest, we can put all of these things together. So this guy, we're going to substitute that in up here for this polynomial. And then we just got to plug in the rest of the numbers. So we already have that, and we can do the math here. I'm going to just give you the answer rather than going through the math in too much detail, so we can see what we can do here. So if you go through all of these things, I am going to combine all of this math here, so 1 over 8 times 6 factorial, and then as well as the 1/2 to the 7/2. And I'm going to combine that in such a way that I end up with the following. And this is probably one of the hardest parts of the assignment, and it's not really hard at all. It's just a lot of work. You have to make sure you keep track of all of your things and keep them in the square root. And you can always check your answers, right? So I could always take this number, multiply it by, 1/2 to the 7/2 and see what that gets me. And then compare that to, I'm going to tell you it's equal to 1 over 384 times the square root of 5. So if this crazy thing that you simplified it down to equals the initial thing, you've done it all right. So we want that. We also always want to have a 1 over a naught to the 3/2. This is in every one of these functions, and so it gives us nice consistency. And the way we get that is by putting the rest of it with the r squared. So here we have basically a naught to the 7/2, and we have r squared, but we're going to take out 4/2 of that, right, which is a naught squared, and combine that here. And this, if you look at the orbitals in the textbook, this is the form that they're given in. So we're going to keep consistent with that form. And then we have e to the minus r over 4a naught. And then we have our polynomial. So let's put our polynomial in, which is simply 1/2 times 12 minus r over a naught. And so you can combine these together by simply multiplying 384 by 2. And that gives us 1 over 768 times the square root of 5 times 1 over a naught to the 3/2 times r squared over a naught squared. It's usually nice to put the polynomial of r in here, so we're switching the order a little bit. 12 minus r over a naught, e to the minus r over 4 a naught. So this is our radial function here, which tells us where the radial nodes are. It should be obvious how to get those, but we'll talk about that in a little bit. We're now going to turn to the spherical harmonic functions. The spherical harmonic functions can be generated based on the quantum numbers now L and m sub L. So with this function, we can generate the spherical harmonic functions. So we have a normalization term out here, and we have a polynomial term here. This is the associated Legendre polynomials, and we can simply get that in a similar way to what we just did for the radial functions. So to start, we have to get the Legendre polynomials, and then we can associate them. So the Legendre polynomials follow this form here. So we have to take L derivatives, which seems scary until you remember that L is simply 2. So we can go ahead and plug in 2 here for L. That's going to give us 1 over 2 squared times 2 factorial times 2 derivatives of x squared minus 1 squared. So in other words, 1/8 times 2 derivatives of x to the 4th minus 2x squared plus 1. And again, this is something that's pretty easy to do. So you can take these derivatives here. You'll get 1/8 times 12x squared minus 4. And then we'll factor out the 4 here to get 1/2 times 3x squared minus 1. To get the associated Legendre polynomials, you plug it into the following formula. So we'll have p L m sub L of x. Now this is going to be equal to minus 1 raised to the m sub L, 1 minus x squared to the m sub L over 2, and then more derivatives based off of m sub L. And so again, what this is going to be for our chosen quantum numbers here is simply minus 1 squared, 1 minus x squared to the 1, and then 2 derivatives of 1/2 times 3x squared minus 1. And so what that's going to end up being is simply 1 minus x squared times 1/2 times 6, or 3 times 1 minus x squared. And remember, we're not taking polynomials of x, we're taking polynomials of cosine theta. So if I want that polynomial, not in terms of x, but of cosine theta, I simply plug in cosine theta for x. So I have 3, 1 minus cosine squared theta. And if you remember your trig identities, you will know that 1 minus cosine squared theta is sine squared theta. So this is how we get our associated Legendre polynomials. And then the rest is just simply plugging and chugging. So plugging in your various L's and M sub L's in here. And what that's going to get us for our function with using 2 and 2, what we get is simply minus 1 squared times the square root of 5 over 4 pi times 0 factorial times 4 factorial. Our polynomial here is 3. sine squared theta. And then we have e to the 2 pi phi. And we could simplify that if we would like to 3/4 times the square root of 5 over 6 pi times sine squared theta times e to the 2I phi. Now, the next step is to make this function real. And we've done some of this in class. It's pretty straightforward. What we're going to do conceptually is mix this orbital using quantum numbers 2 and 2 with the orbital using quantum numbers of 2 and -2, which would be, the only difference would be we'd have e to the -2 I phi. And of course, we can represent e to the 2I phi as cosine 2 phi plus I sine 2 phi. And so if we use the -2 in there, we'll get minus I sine 2 phi, and we can cancel some of these things out. So basically what we're going to be doing is we convert this, when you go through the process, into the square root of 2, and then you'll have cosine of 2 phi, or the square root of 2 times sine 2 phi. And I'm going to choose this one. The other one is just a different orbital. You could totally choose the other one. That's how you get 5 orbitals from these. So then our function of y of theta and phi using only real variables will be 3/4 times the square root of 5 over 3 pi sine squared theta, and then sine 2 phi. To determine the name or the shape of this orbital, right, we need to use some trig identities. The basic thing we're going to do is we'll end up using some of this identity. So to convert from our spherical coordinates into Cartesian, we can use the equation x equals r sine theta cosine phi, y equals r sine theta sine phi, and z equals r cosine theta. So if I had a function that looked like this, I could simplify it into x, y, x, z, whatever I have. And so I'm going to use this functional form here to do that. So I'll take sine squared theta sine 2 phi, and you'll note that this looks nothing like either of those. However, we can use the double angle identity. Maybe you remember that from doing trig a long, long time ago. And that double angle identity says that we can convert sine 2 phi into 2 sine phi cosine phi. And so that means I've got a sine squared theta, I've got a sine phi, I've got a cosine phi, right? That's going to look like sine theta, cosine theta, sine phi. So the variables here, I can represent my sine squared theta and my sine 2 phi with the Cartesian coordinates x, y, which means that this is a dxy orbital. That's where the nomenclature like that comes from. You might be wondering where my r's are, right? And of course, they're right here, right? My r's are all the way up here in the radial distribution function. So they are there, they're accounted for. I'm just kind of skipping over that here. So this is the way that I want you to present the data. So up here, I've got kind of the raw form of the equation that we use. I have all the various polynomials. So I have the numbers you plugged in, 6 minus x, the associated, or the polynomial and the associated polynomial here. And then I have a combination both of the equation before we converted it into a real orbital, so the 422, just straight quantum numbers, and then the one after. This is really just taking our R42 and our Y22 and multiplying them together. So I'm not going to go through that. It's exactly what it looks like. Is we're simply going to plug all of these things in together, and we'll get an answer that looks like this. So now we have the orbital that we are going to use. How do we do the rest of the problem here? The next thing we're going to want to do is to determine the nodes. Now, the nodes are quite simply where the orbital equals 0. And the best way to go about this is to treat all of these things as separate functions. So there will be times where r makes it 0, and there will be times where the angle makes it 0, and those are radial nodes and angular nodes. So quite simply, we can look at this equation and go, oh, well, if r was 12 over a naught, that would be 12 minus 12. That would be 0. So to get the angular nodes, you take your polynomial and you set it equal to 0. There you go. To get your angular nodes, you take your angles and set that equal to 0 as well. So the question would be, what combinations of theta and phi generate 0? And there's not too many options for this, but we can look at this here and go, well, sine is 0 at 0 and pi. And so when theta is 0 or pi, the function will be 0. That will be a node. And sine of 2 phi is going to be 0, again, when 2 phi is 0 or pi or 2 pi, right? So that's going to be 0, pi over 2, pi, and 3 pi over 2. And if you think about what these angles are, right? So theta being 0 and phi, that's the z-axis. And then when phi is 0 and pi, that's the x-axis, and pi over 2 and 3 pi over 2 is the y-axis. So if we have nodes at all of these axes, that's going to be the xz plane and the yz plane. It's not always that simple. Depending on your combination, you could get some wackos in there, but do your best to also try to figure out what these angles mean in three-dimensional space. To determine the shape of the orbital, we simply evaluate the nodes and then select the appropriate orbital from the list provided. So I am going to give you something that looks like this. And you can see all sorts of different orbitals here, right? Now, this isn't every single orbital, right? But this orbital, this is a p orbital. And of course, it could be pointing in 3 directions, but they all look like this. And the same is true for the d orbital. So 4 of the d orbitals look like this, pointing in different directions. 1 looks like this. And then we could even go off into f orbitals and g orbitals and so on. So you're going to have a document that looks like this, and you can just pick one, grab it, stick it in your assignment. So in this case, we have the d orbital with 2 angular nodes. Looks like this, and they're representing perpendicular planes to each other. To plot the radial distribution function, what we're going to do is simply take our radial function and then multiply that by r squared. So you can see there's no y-axis, so I don't care about the y-axis for this. What we're really interested in is where are the radial nodes, and of course, that should be at 12. You can see it's at 12. And you can do this in Excel. I'll go through an example of how to do that in Excel right now. Okay, so I have an Excel document opened up here. To plot something in Excel, it's maybe not as intuitive as it should be, but you have to take and make an x-axis basically. So I have r here, and I'm going to go in increments of 0.5. And we can just go ahead and if you select both of these here, 0, 0.5, and drag it down, you can actually just autofill this. And I'll go to, it depends on the size of your orbital, how far you need to go. I'll go to about 60. And if you need it further, you can just make it further pretty easily. And if you need to make it more fine to make the curve look nicer, you can do that as well. And then we're just gonna go ahead and come in here and plug in the answer. So we've done some of this stuff in lab. It can be pretty tricky to do, but we just need to go ahead and go through the math here. So we want to plot r squared times our radial distribution function squared. So I'll start with an r squared out front, and then we'll go into our radial distribution function. And so our radial distribution function, again, we only care about the r parts. We don't care about anything else. And here, the way that I've done this by having r go from 0 to whatever, if I leave out the a naught, my r is going to be in terms of a naught. So this 1 isn't 1 meter or 1 nanometer, but it's 1 a naught, which is 1 Bohr radius. So we can come in here, and then we'll say that this function is simply r squared again times the polynomial, which is 12 minus r. So we have our 12 minus r, and then we are going to multiply this again by exp. So that's e raised to the -1 times r divided by 4. And so again, in leaving off the a naughts here, I basically, every instance of x, I have x over a naught, I have r over a naught. So my r is in terms of a naught here. We'll close off the parentheses, we'll square that, and now we should get our function. So we'll drag this all the way down here. and we'll see what this gets us. So the gets us 0 at 12. That's a good thing. And the y-axis makes no sense. I've disincluded all of the constants, so that's not really we're not really capturing anything with that there. You could if you were a little bit more careful with your constants, but I don't care about that for you. We'll plot this, with a scatter plot with the line. There we go. Beautiful. Pretty that thing up, and that's going to be our good distribution function here. The last thing to do is to find the average radius of the electron. And to do that, we have to evaluate this integral. We've done that before with more simple orbitals in class. It's the same principle here. I would recommend not doing the integrals by hand. Some of them you can, right? So the R function just give you kind of polynomials. You go look it up in the back of the book. But the thetas sometimes can get hard. So that can make things a little bit tricky. I would like you to go through and show what you should do. So the way I want you to go about these integrals is as follows. So we have our function here. And then I want you to actually write out what these integrals would be, right? So what I've done is the separation of variables. So we have all my constants out front. I have my sine squared to phi d phi, my sine to the fifth, which comes from, right, sine squared times sine theta. So I have all the integrals as if I would do them, and then you just do them using the computer, using the calculator. So my calculator is too dumb to do something like that, but my computer's not. So I went through these on the computer here. So the way that I did this is not necessarily the way that you have to. It's the way that makes the most sense to me. I just simply broke it apart into the constants and then the three integrals. So what I have here is the C is my constant. So this is the constant that we get for our function. Which is, right, 1 over 1024 times the square root of 3 pi. I'm leaving off all of the A naughts, and you can do that. And remember, we've done examples of these in class and in the homework, but our answer is going to be in terms of A naught. It comes from the R integral. So if we go back and look at this here, we have an A naught to the 7th here. Our R integral is going to give us A naught to the 8th, and our angle integral is just going to give us numbers. So that's all those are going to end up canceling out to be just simply 1 A naught. So don't forget that. That's an important component. What we're going to do is just go ahead and evaluate these. So what I have done is I have taken my various functions here. So this is my phi function. So it's sine of 2x. And then I integrated that from 0 to 2 pi, that squared. And then my theta function is sine theta squared. So I have sine theta squared. Took that, squared it, multiplied it by sine x, got an answer. And then here's my R function as well. And that this x cubed here comes from, remember, we have an x coming from this here. We're trying to find the average position, this average R, and then the other R squared comes from the bounds of integration. And so in doing that, I came up with three things. I didn't have to do any integrals myself. I got these numbers, multiplied them all together. I got 21. And that is 21 A naught. All of your numbers should be pretty close together. And if I recall right, they should be in like the kind of like late 20s to 30s sort of number. So if you get one number for one of your orbitals that says it should be 35 Bohr angstroms away, and the next one is 33 Bohr angstroms away, but then you do it for the third orbital and you get 302, that's probably wrong, right? They should all be kind of close together in this somewhat large number, 20s to 30s Bohr angstroms away, or Bohr radii from the nucleus. And that's really it. So once you've got that, you can just put it all together into this form and turn it into me, along with the work that you have done. So there's some algebra, there's some calculus. None of it's too bad. And I think at the end of the day, it's going to give you an appreciation for what these orbitals are rather than just doodles on a paper. And that's my goal.